Hey, what's up, team? Sorry I am not here that day, but I will be here later on. In the meantime, I thought it would be helpful for you guys to see the 2003 FRQs that we assigned over spring break. So here we go. Here is the first FRQ. It is a calculator FRQ that is an area and a volume and all that good stuff. So we're given two functions, looks like. We're given this radx function, and then we're given this exponential function, and they're both being blocked off by this vertical line x equals 1, as seen in the figure here. So the first part, we're going to try and find the region of A. So how do we do that? Well, before I do anything, I probably want to go and find my limits of integration. There is no question that my upper limit of integration is the number 1, but my lower limit of integration is going to be determined by that point right there. So where is that? Well, in order to find that, I'm going to go ahead and set both equations equal to each other. So my limits of integration are going to be wherever rad x is equal to e to the negative 3x. So you can do this a number of different ways. You can go ahead and punch it into your TI Inspire, which is going to be right here. I personally like to graph them both, and I will go ahead and adjust my window. I've got my window settings here. I'm going to go ahead and set my x min to 0, my x max to 1, and I'll go ahead and set my scaling to 0.1. My y min, I'll go ahead and set to 0 just because there's nothing that's going to go below that, at least nothing that I'm interested in. And boom. Okay, so not exactly what I had in mind, but it pretty much captures the essence of the picture, and besides we have the picture with us. So I'm going to go ahead and analyze graph intersection. At this point, these controls should be pretty intuitive to you. So lower bound, upper bound, text, let's grab you, move you up here. So at this point, it looks like 0.238 ... is going to be my x coordinate of intersection. My y coordinate is going to be the 0.48 number. Let's go and write that down. So my limits of integration are going to be 0.238, 734. Whoops, I do not want to block that off. Comma, 0.488. 604. Notice how I am not rounding right now. Not rounding because I want to keep as many decimals as possible so I don't end up with a rounding error. Okay, so to find the area of R, this one's pretty straightforward. It looks like I've got a clear top function here, which clearly seems to be my root function. My bottom function is clearly my exponential. So to solve part A, it's pretty simple. It's going to be from this point right here. I'm going to go and call this A. So it'll be the point A until 1, which is right here. It's just this area. That's what I'm looking at. And my top function is my rad x. And I'm going to go ahead and subtract my e to the negative 3x. Now, remember, you cannot use calculator notation here. You cannot go f1 of x and f2 of x unless you specify what's what here. So if I was to go f1 is equal to rad x and then f2 is equal to e to the negative 3x, that would be okay as long as you specified what it was. But since I didn't until just now, I'll go ahead and leave them as is. Honestly, these aren't particularly complicated functions to write out, and they're not going to take me that long. It's a dx integral since I'm going top to bottom, and at this point it's just a calculator function. So let's go ahead and find out what that is. I'm going to go back to this screen, and remember the shortcut for integration on a definite integral is Shift plus, and I'll go ahead and go. Now I don't get the option of a this time, so I'm going to have to muscle this one out. 0.238734 all the way to 1, and now I am going to go from, whoopsie, wrong button. I'm going to go ahead and go f1 in my calculator, f1 of x minus f2 of x dx. I'm going to go ahead and hit Control, cross my fingers, hit Enter, and I get this 0.4426 number. So let's go ahead and punch that thing in. So I get 0.44. 2 or 3, it doesn't matter, considering the next number is a 6. AP will take either. So there you go. That's part A. Part B. What does it say? Find the volume of the solid generated when r is revolved around the line, horizontal line, y equals 1. Okay, so it looks like we're taking this thing, and we're going to rotate it this way. It's going to go like this. Since I'm rotating it about a horizontal line, this is most definitely going to be a dx integral. And when I rotate this thing, I'm going to get this open space here, which means this thing is also going to be hollow. So I got to keep that in mind. How does that impact my integral? Well, since it's hollow, that means that I'm going to be creating two separate integrals, or two separate expressions that are being subtracted. The inner piece that is being subtracted out of the outer piece. So, how do I do that? My integral is still going to be from a to 1, since I'm doing a dx integral. And remember, I'm going to be inserting a bunch of little hollow disks. They call this the washer method. A bunch of little hollow disks inside. And each disk is going to have a particular volume. Well, volume is pi r squared h. So pi being a constant I can kick out here. My r is determined by my most outer function. Well, my most outer function looks like it's this exponential area, right? Because what I have is I have this piece here that extends from the 1 all the way down. That's the bigger piece that I'm looking at. So how do I express that? Well, 1 is the top piece, right? That's all this space right here, all this space. But I don't want all that space. I want that space. So I'm going to take that 1, and then I'm going to subtract the area underneath that space, which is my e to the negative 3x function. And I'm going to square it because that's my radius. And now I'm going to subtract the inner piece. Well, how do I do that? It's going to be the exact same thing, except now I'm going to go 1 minus the smaller function. And in this case, the smaller function is actually the rad function because there's less space between the red horizontal line and this magenta. Okay? So I'm going to tack on my dx there, go to my calculator, and find out what I've got. So I'm going to go to pi, shift plus, I'm going to go from 0.238734 to 1, and now I'm going to go 1 minus f2 this time, and I'm going to go ahead and square that, minus 1 minus f1, oops, not f minus f1, 1 minus f1 of x, and I'm going to go ahead and square that. Oops, that's not what I want. I do not want that. You see what just happened right there? I want the whole thing being squared, not just f being squared. And so now I go ahead and I just control and I cross my fingers and hit enter. Oops, and I do not have a dx there. There we go. Now I hit control and cross my fingers, and I get my 1.42355 number, and that is correct. 1.423. Okay, so again, outer piece minus inner piece. Part C. The region R is the base of a solid. For each solid, each cross-section perpendicular to the x-axis is a rectangle whose height is 5 times the length of the base of region R. Okay, we've never dealt with this exactly before. However, it's pretty easy to figure out. Cross-sectional volumes, again, it's a dx one. They told me that. Perpendicular to the x-axis indicates dx. So I'm going to go again from A to 1. And so what I've got here is I've got rectangles that are going inside. Rectangles. Where my base is determined by the distance between those two functions. Well, the distance between those two functions is something we've been working with a lot of. It's this rad x minus e to the negative 3x. And that is the base. Now the height is a rectangle that is 5 times the length of the base. Well, how do I show that? 5 times the length of the base. And there you go. Base times height is in the area of a rectangle, and then dx would be the width. So base, height, width, volume. From here, we just punch that into our calculator, and we're good to go. Now, it's easy to look at this actually as, because it's all being multiplied, you could actually see this as rad x minus e to the negative 3x quantity squared times a 5. And in fact, to speed things up in the calculator, it might be easier to see it like that. So let's go ahead and do it. So I'm going to go Shift plus again. Again, my old friend, 0.238734 to 1. Notice I'm not putting pi out here. It's not going to go out there. f1 of x minus f2 of, of x. And now I'm going to go ahead and square that. And I will go ahead and multiply it by 5. It doesn't matter if 5 is in front or 5 is behind. It doesn't really matter. But I just put it in front anyway. Cross your fingers. Control. Enter. 1.55435 ... That is our magic number. So 1.554. So here we go. Hello to you. Hello to you. Hello to you. Pretty straightforward problem, okay? And so, give me a second. I will move on to the next one in just a second. And welcome back for the second FRQ. It reads, a particle moves along the x-axis so that its velocity at a time t given by that function right there. If you need to, please pause and enter that function into the calculator. I will give you a second. Now, it says, find the acceleration of the particle at time equals 2. Is the speed of the particle increasing at time equals 2? Why or why not? So does it make sense, I hope, that if we find v of 2 to be a particular number and a of 2 to be another particular number, we will be good. So let's do it. I already have this in my calculator. It's my newly repositioned f1, so let's go ahead and go back. If I go f1 of 2, I will get, control enter, this negative 2.727 number. So let's go ahead and put that in. Negative 2.727. A of 2, well, how do we do that? Well, that's derivative at a point. So I'm going to go to Menu, Calculus, derivative at a point. My variable is x, my value is 2. I'm taking the first derivative, f1 of x, control, enter for an approximation. It's going to be this 1.587 number. I'll go and write that down. 1.587. Now, notice the speed and, the acceleration and velocity are different signs. So you would then say the speed is decreasing at t equals 2 because velocity and acceleration are opposite signs. And I will go and clean that up right now, actually. I will not handwrite that. Give me a second. And there you go. So, the particle speed is decreasing at t equals 2 because v of t and a of t have opposite signs there. Okay? Sweet. Let's move forward to part B. Find all the times on the open interval from 0 to 3 when the particle changes direction. Justify your answer. Okay, how do we know when a particle changes direction? It's when its velocity goes from minus to plus or plus to minus. So we're looking at the open interval from 0 to 3. So let's go and go to our calculator. I'm going to go to the graph. I'm going to change my window settings. I'm going to go from 0 to 3, and I'm going to go ahead and let it scale by 0.5. Why not? And let's go to OK. All right, cool. So that's what we've got right here. I'm going to go and find out. It looks like this is a candidate right here, but I don't know if it's crossing the x-axis here. You see how it looks like it's kind of close? So I'm going to go and find every single point of intersection. Analyze graph. 0. I'm going to start from the beginning, my lower bound from the beginning, all the way to my upper bound. Oh, it looks like that's the only one that shows up. So it looks like 2.50663 is going to be my place that I'm looking for. So let's go and write that down. Boom. The particle is changing direction at t equals 2.506 because v of t changes signs there. Okay, cool. Let's go and take a look at part C here. Find the total distance traveled. Okay, total distance traveled from 0 to 3. To get total distance traveled, I'm going to go ahead and integrate my velocity. But if I do that straight up like that, I do not get total distance traveled. I get displacement, which can give me some negative area. To get total distance traveled, I'm going to go ahead and include some absolute value bars there. And then we will find out what that number is. So let's go back to this, and we will go ahead and go back to here. Shift plus from 0 to 3. Go to my little MOI. Absolute value, f1 of x dx. Control Enter. Boom. 4.333 or 4.334. Doesn't matter which one you decide to write down. Notice how they're not asking for units. If they are not asking for units, I am not going to try to be a hotshot and create units and get an anti-point. It's just that. Okay. It says, during the time interval from 0 to 3, what is the greatest distance between the particle and the origin? Show the work that leads to the answer. Okay, so this actually involves a little bit of work here. I'm going to go and scroll down. So, greatest distance between the particle and the origin. A couple ways to do this. The way I elected to do it was, you could see its position whenever the particle is stopped. So it looks like the particle is stopped. Particle is stopped at these times. So it looks like x of 0, you know its position. That's 1. And you also know that at x of that 2.506 number. How do you know that? That's because in part B you answered that because in order for the particle to change direction, it had to have stopped. So that is definitely another candidate. So we will find that value. And then another portion would be to test the endpoint x equals 3, or x of 3. So how do we test out this x of 2.506? Well, I'm going to go ahead and integrate from 0 to 2.506 of v of t dt. Well, what do I get? I get v of 2.506 minus x of 0. And I apologize. That should not be a v. That should be an x. Because when you integrate velocity, you get position, not velocity again. So I know now that x of 2.506 is going to equal, by adding this value, this x of 0 to both sides, and we know that x of 0 is 1. By adding the 1 to both sides, I will get 1 plus the integral from 0 to 2.506 of v of t dt. So let's do it. So what I get is I get 1 plus shift plus 0 to 2.506 of f1 of x dx. Control Enter. That is negative 2.265. Let's write that down. So that is going to equal negative 2.265. I'm going to go and not enter, but box that off. That's horrible. There we go. A little better. All right, so now x of 3. I know that that is going to be the integral from 0 to 3 of v of t dt. So that is x of 3 minus x of 0. So I know then that x of 3 is equal to the integral from 0 to 3 of v of t dt plus 1. What does that give me? Using the same method I got before, what I get is I get negative 1.19715, using the exact same thing I did for the 2.506 position. So, here are my candidates. I have negative 2.265, negative 1.19715, and 1. So, clearly, the particle is furthest from the origin at t equals 2.506. So let's write that down. The particle is furthest. Whoa, am I not typing anything now? Here we go. The particle is furthest from the origin at t equals 2.506. And there you have it. That is the second FRQ. Stay tuned. I'll be back with the third one. Alright people, welcome back to the third Calculator FRQ. As you guys know, your AP test is going to be a little bit different. In the past, what the AP test was a 3 non-calculator test, but yours is going to be 4 non-calculator, 2 calculator tests. But either way, this is a good problem to practice, so hopefully you guys will keep up. Okay, the problem reads, the rate of fuel consumption in gallons per minute recorded on an airplane flight is given by a twice differentiable and strictly increasing function r of time t. The graph of r and a table of selected values of r of t for the time interval 0 to 90 minutes are shown above. Okay, a couple things to note. 1, r of t is a rate, right? So r of t is a rate of change. So when we talk about r prime of t, that is the rate of change of a rate. So make sure we keep that in mind. Second thing, the fact that the r of t is a twice differentiable function means that the function is continuous. Okay? And more importantly than that, because the function is continuous, we are dealing with a flight that is non-stop. So anyway, let's get this problem started. Part A. Use data from the table to approximate a value for r prime of 45. Show the computations that lead to your answer. Indicate units of measure. So part A, it looks like we are going to approximate r prime of 45. So what I've got here is I've got r of 50 minus r of 40 all over 50 minus 40. Well, that ends up becoming 55 minus 40 over 10. I'm just getting the values from this table right here. And what I get is 1.5 gallons per minute. Now, because I am finding the rate of change of a rate, it's actually not minutes, but minutes squared. So that's why this whole idea of fuel consumption already being a rate comes into play. So make sure you guys are careful about your units. Part B says the rate of fuel consumption is increasing fastest at time equals 45 minutes. What is the value of r double prime of 45? So what I'm trying to find here is the value right here. Whoops, you can't see that. You're trying to find r double prime of that value. How do we do that? Well, it seems a bit complicated at first, but let me see if I can't logic out this idea for you. Let me go ahead and type this out. Okay, so let's see what this looks like. We know that the rate of fuel consumption is equal to the function r of t. We know that. It told us that. Now, what can we conclude from that information? We also know that, don't do that. We also know that the words increasing fastest, the rate of fuel consumption is increasing fastest. I'll even write that down. The rate of fuel consumption is increasing fastest. What does that mean? Well, that means that r prime of t is hitting its maximum slope. In other words, the slope of r prime of t is going from plus to minus, right? And those words were given by this statement here. Increasing fastest. That's what that's saying. Increasing fastest means that r prime of t is going from from positive to negative. So what does that mean? Well, if we go based on that information, we know that r double prime of t is going from plus to minus, right? The slope of r of t is going from plus to minus, which means r double prime of t is going from plus to minus, and there is only one way that can happen, and that is if r double prime of t must equal 0 at t equals 45. Hopefully that logic makes sense. If not, you can ask me tomorrow and I can go over that portion again. But ponder that for a second, and then we will keep moving with this problem. Okay, part C. Approximate the value of the integral from 0 to 90, r of t dt, using a left Riemann sum with 5 subintervals indicated by the data in the table. Is the numerical approximation less than the value of the actual 0 to 90 r of t dt? Explain your reasoning. Okay, we've encountered questions like this before, so I'm going to go ahead and just draw this out. I've got this happening here. Let's see, at 0, and I'm going by the table here, I'm not going to keep scrolling up and down, I've got 20. At 30, I've got 30. So on and so forth. I'm going to pause for a second so I don't waste your guys' time. Give me a second. And here we go. These are the points right here. If you need to, please hit the pause button. That way you can catch up. Okay, we are going to use a left Riemann sum with 5 subintervals. I've got my 5 subintervals right here. Left Riemann sum, left, left. Again, because it's a left Riemann sum, I am pulling my heights from the left side of the rectangle. Okay, so that's what I got. So let's go ahead and see what this looks like computationally. What this means is I've got 30, right? That's my first base, times my first height, which is 20. Again, height is pulled from the left side of the rectangle. Plus, my next base is going to be a base of 10 times my next height is going to be 30. Plus, my next height is going to, again, be 10. My left height is going to be 40. Plus, my next height is going to be 20 times my height, which is 55. And then my last height is going to be 20 times my left height of 65. So what does that give me? It gives me 600 here, plus 300 here, plus 400 here, plus 5.5 times 20. That's someone buying 20 sports bottles without the clip, so that's $1,100. Plus 650. Well, we never sold anything worth 650 at SeaWorld, so I guess I'll have to muscle that one out. That's just going to be 6.5, which is 13 with 2 zeros. So when you add them all up, you get 3,700. Now, let's think about this for a second. Is this approximation an underestimate? It absolutely is. Why? Because, so this is, let's move this down. This is an underestimate because on a strictly increasing function like r of t, and whoops, that kept going. Let's go ahead and move like down here. A left-hand rule will be under the curve. Some variation of that. Some people will say left-hand rule is an underestimate because R of t is strictly increasing. Either way you slice it, you're good. Okay? Let me go ahead and have you guys pause here if you need to, because I'm going to delete parts B and C. Goodbye. Alright, so let's take a look at part D. Part D is saying between 0 and 90 minutes, with B being the time interval between 0 and 90 minutes, explain the meaning of 0 to B, R of t, dt, and then explain 1 over B from 0 to B, R of t, dt. Well, R of t is the rate of fuel consumption. And because we're strictly increasing, we can conclude that the first piece, this piece, R of t, is the total amount of fuel. Consumed by the plane flying non-stop on the time interval 0 to B. And then this one with the 1 over B, you should know this well, this is the average amount of fuel consumed by the plane flying non-stop on the time interval 0 to B. And there you have it. That is the last calculator problem. I will see you in the non-calculator video. See ya.